interconnection between physics, technology, and society. Physics principles are applied in technology to develop numerous technological devices which are beneficial to society. Laws of electricity and magnetism helped in developing wireless and communications technology. Principles of wave optics paved the way for fiber optics. Fiber optics is used not only in communication but also in interior design. Technological tools and gadgets which are products of physics help people to live as a well-connected society, for example, using phones and other means of communication. Concepts in physics undergo constant study and pave the way for increasingly efficient physical systems, for example, consumer electronic items such as the TV and the computer. Metamorphosis of physics has also led to developing increasingly precision-based instrumentation techniques and tools. Medical diagnostics involves several instruments such as ultrasound machine. Society is so overwhelmingly dependent on technology that we cannot live as comfortably as we do without involving physics. The table gives an idea of how physics and technology are related. Developments in physics has led to a wide range of disciplines linking principles of physics with other subjects like medical physics, geophysics, astrophysics, chemical physics, and oceanography. Within physics itself, sub-disciplines such as mechanics, optics, sound, electricity, magnetism, and modern physics have been expanding their horizons as new discoveries are made. Bioacoustics is a fascinating area in biophysics. It deals with sound systems in animals. In this animation, you see a bat intercepting an insect even in darkness by using its ultrasonic chirp. Laws. Physicists observe natural phenomena, develop theories, and verify them by experiments. As they study, they work with several physical quantities like temperature, density, potential energy, kinetic energy, etc. Most of these quantities keep varying, but some always remain constant. In other words, they remain conserved. Conservation of physical quantities are based on well-defined laws of conservation. Two familiar examples are law of conservation of energy and law of conservation of momentum. If you ride your bicycle all the way to the top of a hill, you need to spend your energy. This energy gets stored up as potential energy in the bicycle. The moment you start coming down the hill, the potential energy starts getting converted into kinetic energy. When you reach the ground, all the potential energy is now converted into kinetic energy. Here, the total energy of the system at any point of time is given by the sum of all energies. One can observe here that the sum of these energies always remains constant. Law of conservation of energy. This law states that when one form of energy changes into another and vice versa, total energy in the system is always conserved. Let us see an example which proves this law. Conservation laws even help in understanding chemical reactions. In chemical reactions, atoms simply rearrange themselves to form products. No new atoms are created, neither are they being lost. Hence, the number of atoms involved in a chemical reaction remains the same on both the sides. Imagine a collision between a car and a truck. Though there may be many forces involved in the collision, we can work out the possible outcomes of the collision by using the law of conservation of momentum. Such estimation helps to prevent collision. Automobile industries use the law in manufacturing vehicles. There are numerous phenomena, beyond any length of human imagination, taking place in the universe involving changes in physical quantities. But still, amazingly, the total energy in the universe is considered to remain constant. Sometimes, old theories and laws are replaced by new ones, as more discoveries are made. For example, until Albert Einstein came up with his mass-energy relationship, E is equal to mc square, total mass of a system was considered to be constant, and this principle was explained to describe chemical reactions and endothermic and exothermic reactions. Einstein's mass-energy equivalence equation, which later paved the way for the production of nuclear energy, served as a breakthrough to the hitherto conventional line of thinking on conservation principles. Although laws of conservation which are applied in different systems can be the same, the quantities involved need not necessarily be the same. In most situations they do differ. For instance, universal law of gravitation, force of attraction between two objects, is directly proportional to their masses and inversely proportional to the square of the distance between them. Can be applied to different systems of objects, but the universal gravitational constant is the same, which is why it is known as universal gravitational constant G. Force of attraction differs from one system to another, depending upon objects' masses and the distance between them. For example, G-force on the Earth is 9.8 meters per second square, whereas on the Moon it is only 1/6 of this value. Conservation laws have helped physicists in new discoveries. One such is the discovery of neutrino, an elementary particle emitted in beta decay reactions. Wolfgang Pauli predicted its emission by applying laws of conservation of energy and momentum. Conservation laws play an important role in explaining the symmetries of time and space in the universe. Physics helps us not only to explain natural phenomena and numerous processes, but also to apply physics concepts in problem solving in the classroom, laboratory, and the world around us. Physics is that amazing branch of science which tries to answer a lot of questions about the universe that we live in. Questions like, how did the universe come into being? Why do the Earth and the other planets revolve around the Sun? Why do we have days and nights? What causes changes in seasons on Earth? What is it that makes us fall down towards the Earth? What is at the heart of any matter? There are millions and millions of such questions that could be answered by physics. Physics is a branch of science which is about the study of such events around us. What is science? Science originates from the Latin word scientia, meaning to know. The Sanskrit word vinyan and the Arabic word ilm also convey the same meaning, knowledge. Science has been termed as a systematic attempt by humanity to understand and explain natural phenomena. This understanding is utilized to harness these phenomena, and if possible, modify them to some extent for our advantage, without any abuse whatsoever. For example, wind energy is harnessed using a windmill. Here, the wind rotates the windmill, which in turn generates electricity. Similarly, the sun's energy can be harnessed by using photoelectric cells. The energy stored in flowing water is harnessed by construction of dams. Here, the flowing water is allowed to pass in hand. Logically, we can classify physics into two broad areas: theoretical physics and experimental physics. The alpha particle scattering experiment resulted in the development of Rutherford's theoretical model of the atom. A beam of alpha particles was generated from a radioactive source. These particles had high energies of the order of mega-electron volts. The beam was then narrowed down using lead bricks. And was allowed to fall onto a thin gold foil. After passing through the gold foil, these alpha particles collided on a detector. Which produced a spark during each collision. It was observed that almost all of the alpha particles were able to pass straight through the gold foil. Very few of them got deviated or deflected back. Since the gold foil was ultimately made up of atoms, this experiment resulted in a theoretical model of the atom, according to which a majority of the portion was considered to be empty. Paul Dirac, who predicted antimatter, was a theoretical physicist. On the other hand, Carl Anderson, who is best known for the discovery of the positron, was an experimental physicist. Whether you take up theoretical or experimental physics, your initial work will be to identify some phenomena, often in nature, observe it, and develop a theory. Natural phenomena can be classified as macroscopic and microscopic phenomena. Macroscopic phenomena include all phenomena and processes which we see in our day-to-day lives. For example, a moving train, an accelerating car, a flying airplane, a rainbow, etc. Microscopic phenomena are those which require highly specialized tools to measure physical quantities. These phenomena describe particles at a very minute level. Suppose you're watching a jet plane flying. Even after the plane disappears, you can see the tracks left by the plane. The tracks show the path traveled by the macroscopic object like the plane. Similarly, even if we cannot see elementary particles like electrons, we can know about their movement from the discharge of a cathode ray tube. Macroscopic phenomena are dealt with by means of the branch of physics known as classical physics. Classical physics itself is a collection of smaller disciplines: mechanics, electrodynamics, optics, and thermodynamics. Mechanics is the branch of physics that deals with movement of particles and rigid bodies. Even propagation of sound in air is a mechanical phenomenon. Sound propagates as mechanical vibrations through the air. Electrodynamics deals with the phenomena of electricity and magnetism associated with charged and magnetic objects. Basic laws of electrodynamics were formulated by Coulomb, Ørsted, Faraday, and Ampere. These laws were put down by Maxwell as a set of equations known to us as Maxwell's equations. The behavior of a current-carrying conductor in a magnetic field, communication by means of propagation of radio signals in the ionosphere, the working of an antenna, etc. are all part of electrodynamics. Optics deals with phenomena involving light. These phenomena can include reflection from a surface or refraction through a medium. The working of telescopes, microscopes, formation of rainbows, etc. are dealt with in the study of optics. Thermodynamics deals with systems in macroscopic equilibrium. It is concerned with change in internal parameters of a system like internal energy, temperature, entropy, etc. Heat engines and refrigerators make use of thermodynamic principles for their operation. Physics in the microscopic domain extends to the atomic level and further. Since classical physics cannot be used to explain all phenomena at this level, quantum mechanics is used. The elegance in physics lies in the fact that most phenomena around us can be explained logically by using physics. Though most phenomena and processes could be qualitatively explained using physics principles, quantitative measurement of these phenomena and processes began to be considered a necessity in the past few decades. This line of thinking paved the way for tools to measure physical quantities with precision and accuracy. This video illustrates how vernier calipers are used in the inspection department of a manufacturing company. In the past 2 decades, laws of physics were found to be universal in application. Almost all natural phenomena are complex manifestations of basic laws of physics. How can we explain such phenomena scientifically? Let's take a simple example. If a coin and a feather are dropped from a certain height, the coin reaches the ground within seconds, whereas the feather takes its own sweet time. If the same activity is repeated by dropping them in an evacuated tube, both of them would fall simultaneously. Air resistance slowed the feather down in the first case. In the absence of air, both the objects would fall at the same velocity. That is, all objects undergo free fall with the same acceleration due to gravity, if no other force acts on them. In this example, we took a real situation, analyzed it, and discovered the basic principle of why a feather and stone fall differently. We considered an imaginary situation and tested it by doing an actual experiment using an evacuated container, and then formulated the theory. All objects in free fall would fall with the same acceleration. This type of testing and formulating theories has always been central to physics learning. Fundamental forces of nature. Physics is a study of forces. All forces which we come across are derived from four fundamental forces: gravitational force, electromagnetic force, strong nuclear force, and weak nuclear force. Gravitational force is a force characterized by mutual attraction of bodies with masses. Here, Earth and the ball attract each other. Gravitational force is universal in nature. All objects exert gravitational force on each other. Electromagnetic forces are forces which exist between charged objects. The animation illustrates electromagnetic force between two current-carrying wires. Electric and magnetic fields are inseparable from each other, and hence the force exerted is known as electromagnetic force. While gravitational force is always attractive, electromagnetic force can be attractive or repulsive.
Strong nuclear force. In an atom, the protons feel a repulsive force from other neighboring protons. Therefore, if there isn't any force holding the protons and the neutrons together, the nucleus will become very unstable due to repulsion. This force cannot be gravity, as gravitational force is very negligible as compared to the electric force. This strong nuclear force is about 100 times stronger than electromagnetic force and is the strongest of all the forces in nature. The strong nuclear force is created between nucleons by the exchange of particles called mesons. The range of nuclear force is extremely small. It acts over distances in the range of 10 raised to minus 15 meters. The strong nuclear force makes the nucleus stable. It does not depend on the charge of the nucleon. It acts equally between two neutrons, two protons, or between a proton and a neutron. Weak nuclear force. The weak force is responsible for radioactive decay called beta decay, during which the nucleus emits an electron and an uncharged particle called neutrino. This weak nuclear force is weaker than strong nuclear force and electromagnetic force. However, it is stronger than gravitational force. It acts over extremely small distances of the order of 10 raised to minus 16 meters.